Hello, everyone. Today, our lecture will be recorded and it will be uploaded in the e-class because of my travel. So in the last lecture, we talked about dark matter at the galaxy scale and galaxy cluster scales. In particular, Coma cluster, we have missing mass, also galaxy rotational curves. We have found an evidence for dark matter, which is required to explain the flat velocity curves in galaxies. So today we are going to discuss dark matter at much larger scales, at cosmological scales. And the dark matter at the cosmological scales, the dark matter is homogeneous, meaning that it doesn't depend on the location and the direction. And so we want to determine the dark matter abundance from the early universe. There are many candidates for dark matter in particle physics. And in the beginning of this lecture on dark matter abundance, we are going to discuss WIMP dark matter. So before going to discuss the details of WIMP dark matter, WIMP weakly interacting massive particle, and we first give you a brief review on the background geometry in the early universe. So this is called FRW background or metric. And we also discussed what is the implication of expanding universe. And also we discussed the what is the equation governing of the evolution of the universe, which is a Friedman equation, and we discuss the fraction of energy density and depending on which component of the energy density is dominant, we will determine the evolution of the universe. Then we are going to discuss equilibrium thermodynamics, and then we are going to discuss Liouville equation that is describing the system with many particles. So we are going to discuss standard model particles and dark matter particles in the thermal plasma. So the Liouville equation in the expanding universe will be the right one to describe the density and the pressure of dark matter, etc. And the Liouville equation, then from there, we are going to discuss the Boltzmann equation for determining for dark matter number density. So first, as I said, let me first give you what is the FRW metric or FRW universes. First, let me see. Is the of course, I think in modern cosmology, we have a best probe for the early universe from the cosmic microwave background and the galaxy surveys, and also uh, the supernova, etc. We have various probes to determine the cosmological parameters. So FRW metric describes the Robert Friedman Robertson-Walker metric describes the homogeneous and isotropic on scales of Hubble volume. The Hubble volume means the observable universe. So homogeneous and isotropic, and on average, we need to introduce maximally symmetric metric. This homogeneous and isotropic universe initially proposed based on the cosmological principle. It's like a Copernicus principle. That means the Earth is not the center of the universe. So similarly, the solar system, the sun is not the center of the universe, and there is no center at all in the universe. Therefore, that means this cosmological principle tells us that the universe is homogeneous and isotropic. There is no preferred position in the universe. And this FRW metric measure the distance space-time interval in this maximally symmetric space-time. So this is the metric on the homogeneous and isotropic space, and here they are T R zeta phi are called moving coordinate, and K is the curvature. When K is +1, K is constant value, and K is equal to +1, it is closed universe, and K equal to -1, it is open, and K equal to 0, this is flat. So this K describes the spatial curvature. The closed means something like this, a sphere. The open is like a saddle. So the space-time is not closed, and the flat is also flat. There is no curvature, and open means this. How to draw this? Something like that. Something like that. I don't know how to draw this. And here the A, T, is the function of this cone moving time, T, and this is what we call scale factor. So because the scale factor factorized and this co-moving metric, so the A scale factor determines the size of the universe. And of course, in the expanding universe, this scale factor is increasing. And for accelerating universe, the expanding universe, the scale factor, the time derivative of scale factor is greater than 0. And if the universe is accelerating, the double derivative is also non-zero. So accelerating means double derivative is greater than 0. So we are living in the universe which is accelerating. So what is the implication of the expanding universe? First thing is that if the chi is the distance in the co-moving coordinate, I mean this is the spatial distance, then the physical distance is we need to multiply by the scale factor to the co-moving distance. Or this is the chi is the co-moving distance. So because of that, the velocity, so a certain position P. So let's say in this conmoving coordinate, we need to define the center. So the origin of this spherical coordinate at r equal to 0, the observer, our observer is located at the origin. And then point P, we have this is the conmoving distance, chi times the scale factor. If universe is not expanding, just the physical distance is the same as the conmoving distance. So this is the chi is the distance in r zeta phi. Then if you take the time derivative of the physical distance, the chi, this conmoving distance, is independent of t. So we have got this result, which is the a dot over a times a chi, which is the equal Hubble parameter h times physical distance. So therefore, the velocity, so moving away from us, v, is due to the expanding universe. So for instance, galaxy located at P will receding from us with a velocity v, which is determined by this formula. So this is the distance, luminosity distance, or physical distance. And this is the v, is the receding velocity. And h is the time derivative of scale factor divided by a, which is the Hubble parameter. Since the universe is expanding, the Hubble parameter is greater than 0. So that means the galaxy is getting away from us in proportional to the physical distance. So this is the Hubble law. So this is the first aspect, implication of the expanding universe. And the second implication is that the wavelengths, suppose the wavelength is given by lambda, which is the, in quantum mechanics, you can relate the wavelengths to the inverse momentum. So the Broglie formula, wavelengths. And the physical, as I said, the physical distance should be multiplied by the scale factor. So the wavelength is proportional to the scale factor, the physical distance. Therefore, the wavelength at present the ratio of the wavelengths at present to the wavelengths in the past, given by this, the ratio of the scale factor. So A0 is the scale factor at present. Normally, we normalize the scale factor equal to 1 at present. And this A in the denominator is the scale factor in the past. Suppose the the light with the wavelengths emitted at time t, then the scale factor is given by A of t. Then this A, the scale factor at the time of emission is smaller than the scale factor at present. Therefore, the scale factor, the wavelength present at lambda 0 is what we are observing at present is given is larger than the one at emission. So this is we call the redshift. The wavelength becomes larger at present. So that is the second implication of the expanding universe, and also the energy density if the matter, for instance, matter is the pressure matter, pressureless matter, P equal to 0, then total energy density will be given by the volume of space-time times energy density. So this rho is the energy density. Then from the energy conservation, we found that the time derivative energy density changes due to the change of the scale factor. So this is Hubble parameter. Therefore, the energy density minus 3 h rho, which is small. So energy density decreases in time. So this is the third implication of the expanding universe. Now we are going to discuss what determines the evolution of the scale factor. There are two equations to determine the evolution of the scale factor. What determines the evolution of the universe? It depends on the type of the energy component in the universe. And since we are considering homogeneous and isotropic universe, therefore, if there is non-zero energy density, then energy density and pressure, most of them depends on time only. There is no space there's no dependence on the spatial coordinate. So then the dynamics of the scale factor AT determined by the Friedman equation, which is given by this formula. And here the H square is, as I said before, this is the Hubble parameter square. And this K is a curvature. So K equal to +1 or -1 or 0. And this M Planck is the nothing but one over 8 pi g, Newton constant. G is the Newton. So surely if the energy density, so energy density is positive, which is the case, then the curvature is 0, the flat universe, and certainly the scale factor h0 h square is always greater than 0. So of course in this case a dot equal is greater than 0, or a dot is smaller than 0. So the first case is expanding universe, and then the second case is the contracting universe. So we are taking the expanding universe, and this another equation that governs the energy density, which is the continuity equation. That is the given by this one. This formula. So this is nothing but total energy, the H is cube times energy density is given by minus the pressure times the D A scale. So this is a cube is the volume. Therefore, the left-hand side is the change of the total energy. On the right-hand side is the work done by the universe. Okay, the work done by the expansion. So then you can show that this is this one, because dt, we have dt in both sides. The change in the energy is given by the work done by the expanding universe. So this is nothing but the energy conservation. So then you can use these two equations, the energy conservation and the equation motion for the scale factor. You can determine you can fully determine the dynamics, the evolution of the universe. So the first equation we call Friedman equation. Now we have discussed the Friedman equation and continuity equations. Also, we also define the fraction of the energy density. Let's take the Friedman equation. And then we divide both sides by h squared. And also we define the critical energy density, rho c equal to 3 m Planck scale times Hubble parameter. Then the energy, the fraction of the energy density defined by omega. Omega is the rho divided by rho c. Of course, this rho is the total energy density. So let me define this omega equal to total energy density divided by the critical energy density. Then the Friedman equation becomes like omega minus 1 equal to k over h squared times a squared. Then for k equal to plus 1, which is the open, this is closed universe. Closed universe, then omega is the omega minus 1 is greater than 0. So omega is greater than 1. If k equal to 0, that is the flat universe. Omega equal to 1. If k equal to minus 1, which is the open universe, then omega is smaller than 1. So there are 3 cases. According to the current observation, omega equal to 1, flat universe is favored. So we can ignore the special curvature from now on. So what if the universe has a positive curvature, k equal to +1, according to the Friedman equation, if you move the curvature term to the right-hand side, you have this equation. And some point, the first term is positive, and the second term is negative. Positive, and second term is subtract the negative. These two contributions can vanish. Then the derivative of the scale factor becomes 0. So in the beginning, universe is expanding, and now there's no choice but to contract. So there's a contraction. So one can draw the scale factor as a function of time. Then the scale factor, in the case of closed universe, the scale factor increases, and at some point, the scale factor reaches the maximum, and then it decreases. So this is the closed, because of that, this is closed universe. Because it is the finite universe. The volume of the space-time is finite. And when it is flat, omega, so this is omega, greater than 1, for the flat, for the closed universe. So omega equal to 1, that is the flat universe. Flat universe, if k equal to 0, then the second term here vanishes, and then the universe keeps increasing, and the scale factor keeps increasing. And if the omega is smaller than 1, then scale factor, so if k is a negative, then you have an extra contribution to the total, effective total energy density due to the special curvature. So because of the universe expanding much faster than the case with the flat curvature. So this is open. Third case is the open. Okay, now depending on the value of the omega parameter, we can see what is the evolution of the universe. But currently, according to the observation, the flat universe, the omega equal to 1 is favored. And the next thing is what is the evolution of the energy density or the scale factor as a function of time. So it depends on the dominant, what is the dominant energy component is. So there are three kinds of energy densities. The first is the radiation. So radiation means the relativistic particle. If the relativistic particle is dominates, then the pressure for the system with the relativistic particles is given by the 1/3 times the energy density. And if it is the particles in the system is matter, meaning that the mass of particle is larger than the kinetic energy, non-relativistic particles, then in that case pressure is 0. And when the vacuum energy is dominant, the pressure equal to -ρ. So then from the continuity equation, by the way, we can parameterize this is the relation between the pressure and the energy density. We introduce the W, the proportionality constant between pressure and energy density. So this is the equation of state. Then for radiation, W equal to 1/3, and matter W equal to 0, and the vacuum energy W equal to -1. In general, the W could vary between -1 and +1 for normal case, but here just we are choosing typical value of the equation of state. So according to the continuity equation, we have this equation, the time of evolution of the energy density given by this, the sum of the energy density and pressure. So if you plug the equation of state P equal to W rho, then the continuity equation becomes like this one. Right, and this is H is the scale factor A dot over A. Therefore, rho must be proportional to A to the -3 times 1 plus omega. Then the scale factor, the energy density scaled by inverse power of the scale factor. So for matter, for radiation domination, omega W equal to 1/3, then energy density is scaled by A to the -4, and matter domination W equal to 0. The energy density is scaled by -A to the -3, and then vacuum energy lambda dominates, and the W equal to -1. Then scale factor is constant. The energy density becomes constant. So given that the scale factor dependence of the energy density, we can use the Friedman equation to determine the scale factor as a function of time. So let me take the flat universe. Then the Friedman equation becomes like this. Of course, the total energy density rho is the sum of the radiation and matter and the vacuum energy in general. But if there's radiation domination, the radiation energy density is much greater than the other two, then total energy density can be approximated by the radiation energy density, which is scaled by 8 to the minus 4, according to this result. Therefore, in this case, we can use this scale factor dependence in order to solve the Friedman equation. So Friedman equation, therefore, becomes a dot over a scale is a scale by a to the minus 4. That means a dot scale by a to the minus 2. So that a dot is the inverse. Therefore, I think that you can show that and show that so this is the integral, so we can integrate independently for a and time, and then you will get the a scale is proportional time. Therefore, scale factor is proportional to the square root of time in this case. So this is case for radiation. Similarly, you can obtain similar result for matter dominates. So matter dominates much greater than the other two, right? And then the total energy density is approximated to the one for matter, which is scaled by 8 to the minus q. So again, you can use the Friedman equation is proportional to the matter energy density, which is the 8 to the minus q. Therefore, a dot scale is proportional to a inverse a, and a dot is the 1 over square root of a. Therefore, we can do a similar separation of integration, and this is nothing but this one. Therefore, the scale factor is proportional to t to the 2/3. Okay, in comparison to scale factor is proportional to the square root of t for radiation. So exponent is a larger than the one for radiation. So in the case of matter, in the case of matter domination, universe increases more rapidly. expands rapidly, more rapidly, rapidly than for radiation domination. So this is the meta domination that we are thinking of. The meta domination, the universe expands more rapidly than for radiation. Finally, for vacuum energy domination, vacuum energy is much larger than the other two, radiation and matter. Then total energy density is approximated to the one for vacuum energy, which is constant. So the Friedman equation again, A dot over A square is constant. Let me call this constant H0 square. Then from there, A is proportional to the e to the h0t. So there's an exponential. The scale factor is exponentially growing. So vacuum energy dominance, so in this scale factor dependence during inflation, this is the early period of exponential expansion before the standard Big Bang cosmology, or dark energy at present in the current universe. So there are two periods of exponential expansion in the early universe or late universe, the vacuum energy, if the vacuum energy dominates. So let me summarize these three. In the one plot, let's take the log of energy density and log of scale factor, and the radiation domination, scale factor as a function of t, log of t. The radiation and domination, sorry, I wanted to tell you. So energy density is the function of scale factor. So radiation energy density scaled by a to the fourth, matter energy density scaled by a to the minus 3. Vacuum energy is it's constant. So radiation decreases faster than the one for the matter. So in this logarithmic scale, you can draw something like that. Something like this. And so the first one is the radiation, and second one is matter, and third one is constant. It's the constant value. So this is the vacuum energy domination. The current universe is dominated by vacuum energy. So we are here. This is log of H at present. And here, there's point where the radiation and matter, they are equal. So this is the log of A equal. That means radiation energy density is equal to matter energy density. The matter radiation equality. And so with respect to this matter radiation equality, to the left, the radiation, sorry, to the left, this region is the radiation domination. On the other hand, to the right, the matter domination. And here, at some point, is vacuum energy, lambda is dominant, so in this region. If the vacuum energy doesn't change the energy density, just vacuum energy will keep dominating. So this is lambda. So there are two boundaries. So until now, actually, I have finished the basics for describing the early cosmology. And now it's time to think about equilibrium thermodynamics here. So when the equilibrium thermodynamics equilibrium thermodynamics. So when the particles in the system in thermal equilibrium, they are sharing the common temperature, and then we can define what the average number density, what the average energy density, what the average pressure, etc. So so then we can relate, let's say, energy density and pressure, they are all function of temperature, and we can relate with that information when the system is thermal equilibrium. With that information, the energy density pressure is a function of time. We by using the Friedman equation, we can relate temperature to the cosmic time. This T is the cosmic time, and this capital T is temperature of the system in thermal equilibrium. So initially, the number density of particles is very large because the universe is so small, so that the distances between particles are short. They are interacting more often to be in thermal equilibrium. So in the old universe, the system with many particles must have been in thermal equilibrium, so that we can apply the equilibrium thermodynamics as we learned from the class, undergraduate class on statistical mechanics. So let me first tell you, give a review on the phase space distribution. Or occupancy distribution for the for dilute weakly interacting gas. Or particles. Then this phase space distribution is a function of momentum, which is given by this quantum statistics. And here for plus sign for Fermi-Dirac statistics, so half integer spin. And minus the Bose-Einstein statistics, which is the integer spin particle. And here the E, capital E is the energy, and mu is the chemical potential. So we are assigning the chemical potential +1 for Fermi, for particle, for satisfying Fermi-Dirac statistics, -1 for Bose-Einstein statistics. So in equilibrium, for gas or particles in equilibrium, we can determine what is the probability for particle to be in a state with energy and the chemical potential. So this is the temperature. We can determine the phase space distribution as function of temperature. And this energy, because it is weakly interacting, so this energy can be approximated to just energy for free relativistic particles in general. So just you only have to know the mass of particle, then the phase space distribution is fully determined. So with that information, we can compute the averaged number density and also averaged energy density as well as the averaged pressure. Etc. And here I forgot to say that so let's say G, we denote the number of degrees of freedom each particle by this G. So if it is electron, then spin up and down, so G equal to 2, for instance. If it is photon, there are 2 polarization states. So in that case, also G equal to 2, for instance. So when we count the number of density, we need to multiply by this number of degrees of freedom. And then we integrate the phase-based distribution over the momentum, 3 momentum. So this is the definition of the number density, average the number density. And the energy density also just weighted integral with the energy. So energy is function of momentum. So this is energy, and the pressure also similarly defined by this weighted integral. But there's some non-trivial factor here. Now momentum scale divided by 3 times energy. So this is the kind of the so this factor account for the energy density. And so account for the pressure. So then in principle we can integrate over the phase space distribution with some weight factor. And then the calculation will be more or less straightforward. Okay, then we will continue to discuss this part in the next lecture. Okay, thank you.